Hey there, how you doing? Terry Brown, Mechanical Engineering here with another Engineering Mechanics video solution. This time we're going to look at trusses. All right, so here we have a typical truss type problem. So in this case, we're told that the truss is used to support a balcony and is subjected to the loading that's shown. So if we look at this truss here, we can see that the truss members aren't pinned at each end. So we have to make the assumption in order to use our truss analysis that these end connections here are such that we can approximate them to a pin. For this simple problem, or this simplified version of the problem, we're going to assume that the ends of the truss members here are pinned. So what we need to do is to work out the force in each member and state whether each of the members are in tension or compression or maybe even zero force members. Right, so we're given the values for the loads and also the dimensions. So as you probably know, there are two methods of solving pin jointed truss problems. Firstly, the method of joints, which we'll do first in this solution, and then the method of sections. So we'll make use of both of these. Firstly, we'll just do the whole problem using methods of joints, and then we'll check our solution by using method of sections. Okay, so to start with, we'll draw a free body diagram of the truss, and that will enable us to determine the reactions at the supports. Now, it is possible to determine the forces in the members without drawing a free body diagram of the entire truss and working out the reactions at the supports. But in any real practical problem, you're going to need to know those values anyway. So let's do it. And then when we use our method of joints, we can compare the results that we get with the values that we calculate for our reactions. Okay, so we'll start with something that we know. We'll treat the entire truss as a rigid body, put in our values. So our rigid body, free body diagram over here. Now we need to just put in the reactions that are generated by the supports over here. Now, down the bottom here, right, this is a pin connection, but I'm pretty sure I only put a horizontal force here. Right, yes I do. So let me go back and explain why. So previously, you should have looked at two force members in equilibrium. Okay, so if we're assuming here that if it's pin connected at D here and pin connected at E, then assuming the weights of the members are negligible for now, then this is a two force member. Right? So we've got a connection here, pin connection at E. We've assumed a pin connection at D, so therefore this is a two force member. And if it's a two force member in equilibrium, then the force acting on this member at these 2 points, the force here at E must be equal and opposite the force here at D, right, and collinear. So that's why I can put this reaction force here as a horizontal reaction force only, right, without a vertical one. Even though this is a pin connection, and normally we would have a horizontal and a vertical pin connection like we have at C, but here, because DE is a two force member, we can draw that there. All right, so you can try and work out the sense of these reaction forces. So you can see I put an arrowhead on REX here, and I've done that by looking at point C, and imagine that I'm taking moments about point C. So the two forces here cause no moment about point C. We've got our two loads out here tending to rotate this truss anti-clockwise about C. So if they push down here, it's going to rotate anti-clockwise about C. So therefore we need a force down here to push back around clockwise. Okay, so therefore REX has to be acting to the left. Having found that out, we can then put on that the horizontal component at C must be to the right because there's no other horizontal forces. So therefore, in order for this to be in equilibrium, this has to be acting to the right. You know, if we had other horizontal forces acting elsewhere, then we couldn't be so sure about this. But in this case, we've only got the two, so therefore they must be equal and opposite. And then for the vertical reaction force, right, we've only got these two vertical forces acting. So acting downwards. So therefore this one must be acting upwards. Sorry, I've been a bit unwell. I've had a bit of a cold or flu lately, so please excuse my voice and croakiness. Okay, so let's put some labels on those two unknowns. We'll call them RCX and RCY. All right, so then to start working out these unknowns, we have our three equations of equilibrium, sum of the moments and two sum of the force equations. And as usual, we'll apply the moment equation first, look for a point where two of our unknowns act through. So in this case, it's point C. So RCY and RCX have zero moment about C. So that will enable us to work out REX straight away. So we'll start looking at the moments of each of the forces. So we have P1 times 2A. Okay, perpendicular distance from P1 to C. So P1 times 2A. Is it clockwise or anti-clockwise? As we discussed before, they're tending to rotate about point C in an anti-clockwise direction, so therefore positive. And then we have P2, perpendicular distance to C is A, and then we have REX times its perpendicular distance here, which is A, and tending to rotate clockwise, as we discussed before. Put all that equal to 0, and we can solve for REX. In this problem, we could have actually used one of the force equations to find something straight away. We could have used sum of the forces in the vertical direction because the only unknown in the vertical direction is RCY. So we could have just done RCY equals P1 plus P2. But anyway, let's have a look and see what I did next here. So I did sum of the forces in the horizontal direction. Right, and now that we've worked out REX, and as we kind of thought through the problem before, we could see RCX will be equal and opposite to REX, 8 kilonewtons for that one. And then, as I just discussed, sum of the forces in the vertical direction equals 0. So RCY will be P1 plus P2, which will give us 5 kilonewtons. Okay, so that's just our rigid body equilibrium applied to the whole truss as a single rigid body. All right, so now let's start to have a look at applying the method of joints and start to analyse the individual members of this truss. Okay, so I've just redrawn the whole free body diagram over here again, just for reference. You don't need to redraw it. I just put it on my following page here so I don't have to be flicking backwards and forwards. When you're applying the method of joints, there's what, 1, 2, 3, 4, 5 joints here. Which one do you start with? Start with the simplest one, I guess, where there's a load applied, right? So as I was saying before, you don't actually have to work out these reaction forces in order to apply the method of joints. So if we go over here to joint A, we've got one force applied and two members attached. So here, if we apply our force equations of equilibrium, we should be able to work out these two unknown forces. Whereas if we did a free body diagram of point B here, we're going to have 3 unknown forces. Right? So we won't be able to solve for anything straight away. Down here at point D, we'll have 1, 2, 3, 4 unknown forces and known input. Right? So we're not going to be able to solve for anything there straight away. So point A is where we start from. Drawing our free body diagram, just a dot to represent point A. Then we have our known load. And then we have some forces acting on this joint through the truss members. Okay, and because they're pin connected, or we've assumed that they're pin connected members, they're all 2 force members in equilibrium. So we know that the force here is going to be along the line of the truss members. Okay, so we can put in our force directions. And now we can just start to look at it and work out whether this is going to be up to the left or down to the right, whether this is going to be to the right or to the left. And we can do that by thinking through the equilibrium equations. So if we look at this one here, we can't tell the horizontal direction straight away. But if we look at this force here that's at an angle of 45 degrees, we can see that the vertical component must be acting upwards for some of the forces in the vertical direction to be equal 0, right? Because the only other force we have is P1 acting downwards. So therefore that force there has to be up to the left. And now that we know the sense of this one, the horizontal force must be acting to the right to balance the horizontal component of this force here. Now, if you're unable to do that, and if you're just starting out with particle equilibrium and trusses and so on, then what I suggest that you do is to just assume everything is positive. Okay, and positive means directed away from the joint. Okay, so just assume everything, all the members are in tension. And then if you do your algebra correctly, write your equations and then do your algebra correctly, the members that are in compression will come out as negative answers. Now that we've done that, let's label our unknown forces. So I'm just going to call them FAB, so force from A to B, or force for member AB, and FAD for member AD. And now we have a pretty simple particle equilibrium problem. Sum of the forces in the vertical direction equals 0. So we need to do this equation first so we can find out FAD and then when we look at horizontal forces, right, we'll have a known value to put into the equation. I've done a bit of a shortcut here. So let me write in for you the steps before the shortcut. All right, so sum of the forces equals 0. So we have P1 minus P1 plus FAD sine 45. And we know sine 45 is equal to 1 on root 2. Okay, so therefore we have minus P1 plus FAD on root 2 equals 0. So if we rearrange that equation, hopefully you can see how we go from there to there. Right, so if you're not confident to be able to just look at the triangle and do this root 2 or 1 on root 2 thing, then put in the full equation. Okay, so there we have putting in our value for P1 that we were given. FAD is 3 root 2. All right, so now doing sum of the forces in the horizontal direction equals 0. And again, I've just done a bit of a shorthand here. So you could write, of course, FAB minus FAD cos 45. Okay, cos 45 is equal to 1 over root 2 as well. Okay, so FAB will be equal to FAD over root 2. Right here, just substituted in here FAD. Right, FAD equals root 2 P1. So root 2 P1 into here, root 2 over 2 is 1. So we just end up with P1. That's equal to 3 kilonewtons. Now thinking about the forces on the members that are connected to this joint A. Okay, so what we've got here is the free body diagram of the pin of point A, and then we've got these truss members attached to it. The force that we see here on the free body diagram of pin A, so this force is the force that the member AB exerts on the pin. Then if we draw the member AB, we see equal and opposite to the force over here, right? The force that the joint or the pin exerts on the member. And then on the other end of that, for it to be in equilibrium, must be equal and opposite to this, right? So hopefully you can clearly see now that this is in tension. And we could do the same thing for member FAD. Okay, so if that's member FAD, then we need to have equal and opposite to this over here, right? So we'll have a force here like that. And then, of course, at the other end, we need to have equal and opposite again. Right, so hopefully you can see that that's now in compression. Right, so if we have a force, so when we do our method of joints, if the force is pushing into the joint, then the member is in compression, because equal and opposite to what's happening on the joint is happening on the end of the member here, or the truss member. And so here we have this force here, equal and opposite to the force that we've got shown acting on the joint. Okay, so this is pushing in here and then equal and opposite at the other end. So you can see that this is in compression. Whereas over here, if the force is pulling away from the joint, then equal and opposite over here on the member pulls away from the end of the member. So therefore this is in tension. Looking now at our free body diagram of point B. So now that we have the force AB, we can use that as an input into our free body diagram at point B, where we originally had 3 unknowns, but now that we know FAB, the only 2 unknowns will be FBD and FBC. Right, so here's our free body diagram, forces in the directions of the truss members. So pretty easy to work out the sense of this force, FBD, no other vertical forces. So if we've got P2 acting downwards here, then this force must be acting upwards. And over here, we need to now put on the force that's exerted by the member FAB. So here we need to put equal and opposite to what we've got here on joint A, or might be easy for you to think of that we have to have equal and opposite to what we've got here at NB of this member AB in tension. Okay, so down here we need to put the arrow acting to the left. And now that we know that, and we note that FBA was FAB, you can just call them both FAB if you want, doesn't really matter. The force on the other side in member BC must be equal and opposite to that, so therefore must be acting to the right. Okay, and again we can draw our free body diagram of member BC and see that that's in tension. So looking down here, if this force FBD is pushing upwards, then equal and opposite on the member at B must be pushing downwards. Okay, so member BD is in compression. Right, so some of the forces in the vertical direction equals 0. So this one's pretty easy. Right, FBD equals P2, which was 2 kilonewtons. And some of the forces in the horizontal direction equals 0. So we calculated FAB before. So FBC will be equal to FAB, which was 3 kilonewtons. Okay, so that's for joint A and joint B, which has now given us the forces in members AB, BC, BD, and AD. So now we need to look at a diagram of point C. We could go down to a free body diagram of point D or joint D down here, which we'll do in a second, just as a check. But for now, we're going to look at joint C, and we can do that in this case because we have found our external reaction forces. Right? If we hadn't done a free body diagram of the whole truss and worked out our reaction forces, then we would need to do free body diagram of joint D first. And then we could do the free body diagram and equilibrium equations for the whole truss to check. Here we know our external forces acting on the joint. We do actually know the direction of the force BC because we just calculated it in the previous problem. But if we look at this one that we don't know first, we can see we've got only one other vertical component, which is the force RCY that we calculated before. So therefore we can see that the force down here must be down to the left. Right? And then we can put in equal and opposite to what we calculated before for the force in BC. All right, so labeling all our unknowns, right, RCX and RCY we calculated before from our rigid body equilibrium over the entire truss. So some of the forces in the vertical direction equal 0. So we have FCD. So if you want to think about this step backwards, RCY will be equal to FCD sine 45. And sine 45 is 1 on root 2. Right, so FCD over root 2 equals RCY. So that gives us 5 root 2. Then some of the forces in the horizontal direction equal 0. So we have 3 components here, RCX, FCB, and FCD cos 45. Okay, and we just put FCD over root 2, right, instead of writing cos 45. And do the calcs and we get FCB equals 3 kilonewtons, which matches what we calculated on the previous page. That is one check for our solution. Okay, and member CD is in tension because we can see that the force here is pulling away from the joint C. So therefore equal and opposite on the end of the member CD must be pulling upwards Right, so therefore stretching it, putting it in tension. Okay, so let's do a free body diagram of point D and check using that. So drawing our free body diagram. Okay, so I've started here with FCD or FDC equal and opposite what we calculated up here. If you'd done the problem where you hadn't calculated the external reactions first and were just making your way through the problem using method of joints, then your known input into the problem after having done equilibrium at joint A and then B would have been the force in member AD and the force in member BD would be your known inputs. And then you would be able to then calculate FDC and FDE. Here I've just put in FDA, which is equal and opposite to FAD that we calculated before. FDB, equal and opposite to what we calculated on the previous page. And our only unknown in this case would have been the sense of the force FDE down here. But we can see that this has to be acting to the left, right, because we've got FDA to the right and FDC to the right. Okay, so putting in our 45-degree angles there, some of the forces in the horizontal direction equals 0. So we have FDE equals the horizontal components of FDA and FDC. Okay, so sine 45, so 1 over root 2. And just repeating what we calculated before, so I've just put these in here. Right, we calculated these on the previous page, so we can substitute these into this new equation down here, and we get FDE equals 8 kilonewtons, right, which corresponds to what we calculated before for REX. So that checks out our solution. All right, so we can now summarize our final answers. FAB, 3 kilonewtons in tension. FBC, up here, also 3 kilonewtons in tension. Okay, so what you might like to do is to just note all of those where they're in tension and compression. Okay, so hopefully, you can kind of visualize members and whether they're in compression or tension, right? So, these forces are pushing down here and this is reacting in here, right? So this one's going to be in compression, pushing back against this force down here. All right, so that's the end of the first part of the problem, solving it by method of joints. So we'll now go and have a look at using method of sections. Okay, so when we do method of sections, right, we look for a section that will cut through 3 unknowns, right? We can't cut through more than 3 members because then there'll be too many unknowns. So in method of sections, we'll be using the 3 equations of equilibrium. To do method of joints, you need to know your particle equilibrium really well. To do method of sections, you need to make use of rigid body equilibrium. Okay, so and you should know that the 3 equations of equilibrium for rigid bodies is the 2 force equations plus the moment equation. Only 3 equations, so you can only cut through 3 members. You can cut through 2, but then it kind of becomes just a method of joints, really. And we'll see that as we go through. So I'm going to cut through those 3 members. If we cut down through here, we'll have an unknown force in DE, an unknown force in CD, and an unknown force in BC. So we should have enough equations to solve for the unknown forces. All right, so drawing my free body diagram of one side or the other of the cut. So let's assume that we haven't calculated the reaction forces. Often in textbook problems, they'll just say, I use the method of sections to find the forces in joints BC, DC, and DE. Right? And if that's all you're asked to do, then you don't need to work out the reactions, right? You can, as you'll see, by taking a cut through these 3 members, we've got some loads out here. We can calculate our unknowns. Right, but in a real practical problem, you'll never just want to know the force in only 3 members. You want to know the forces everywhere, right? So you've got to do the whole truss. But anyway, let's do now the method of sections on this bit. So we've got now a free body diagram of the left-hand side of the cut as a whole rigid body. And we're now going to apply the equations of equilibrium for that. So remembering that each of these members are two force members because we've assumed pin connections. We know that the forces at each end are going to be just along the lines of the three members. Okay, so there's no bending in here. In reality, because we've got these bolted and gusseted connections, there will be some bending, but we're ignoring that for this problem. Right, so we have forces directed along the lines of each of the truss members. Okay, so you can just assume the sense of these forces, or you can try and work them out, right? Or just make them all in tension, and then if you get a negative value, then that'll tell you it's in compression, right? But I usually like to try and work them out. So if we take moments about point D, for example, then this force around here is tending to rotate anti-clockwise about D. So therefore, the only other force that's going to cause a moment about point D will be this force up here. So that will need to be causing a clockwise moment. So therefore, this force will need to be acting to the right. I've labelled that one RBC. And then the next one I've done is this one. Right, so if we look at this one, this has a vertical component. So the only other vertical forces are the two applied loads which are acting downwards. So therefore this one has to be acting upwards. And then our force down here, so these two forces are acting to the right. So therefore this force here must be acting to the left. I'll label that other force first. Right, so this one down here acting to the left. So that's how we determine our internal forces that are acting in each of the members. If you can't do the thought experiment by looking at moments to work out your force to start with, then just make them all positive or tension, and then your algebra will tell you which ones are in compression. All right, so taking moments about point D. Right, we take moments about point D because two of our unknowns lines of action pass through point D. So therefore they won't appear in the equation. So our only unknown will be RBC. So we have P1 times A minus RBC times A as well, all equal to 0. Rearrange our equation and we get RBC equals P1 equals 3 kilonewtons, which I think is what we had before, or it should be, pretty sure it is. And that's in tension. Okay, so you can see that up here. So that's pulling on the truss member here, so therefore in tension. Okay, so now let's apply our force equations of equilibrium. Sum of the forces in the vertical direction equals 0. Right, so we just have the vertical component of RDC and our two applied loads here. So RDC over root 2. Again, remember RDC, what we're doing vertical, so cos 45, which is 1 on root 2. So RDC on root 2 minus P1 minus P2 equals 0. So we get RDC equals 5 root 2 in tension. Force is pulling away from the truss member here. Sum of the forces in the horizontal direction equals 0. We have RBC, the horizontal component of RDC and RDE. So RDE is our only remaining unknown. Solve for RDE and we get 8 kilonewtons, okay, which is the same as we had previously. And it's in compression, right? We can see the force here pushing into the truss member, so therefore in compression. We could take an alternate cut. So I'm just showing you this as an alternate way of, so if you get the cuts wrong, well, not so much wrong, but different, let's see what happens. So taking cut 1, again, we've only cut through 3 truss members. Okay, so we should still be able to calculate for all of our unknowns. We put on our force directions. If we take moments about point B, or imagine we're taking moments about point B, P1 is tending to push down around anti-clockwise, so therefore the force in AD needs to push up here around clockwise for it to be in equilibrium. Okay, so that gives me the sense of one of my unknowns. Then looking at our other forces, so this is the only, apart from unknown force over here, the only other horizontal force is the horizontal component of this force that we've just found. It acts to the left, so therefore this one up here must be to the right. And if we take moments about point A, this force here is pushing downwards, causing a clockwise moment, so therefore this force pushing up here has to be causing an anti-clockwise moment. So therefore that's why it's upwards. Right, give them all labels. Apply our equations of equilibrium. So taking moments about point A, the only forces that are causing moments are P2 and RBD. Right, so it's RBD times A minus P2 times A. So I've just done a shortcut here. So RBD equals 2 kilonewtons in compression. And then some of the forces in the vertical direction equal 0. So RAD, the vertical component here, is RAD sine 45, or RAD over root 2, minus P1 minus P2 plus RBD. So we can solve for RAD and get 3 root 2. Right, we can see that force is pushing into the member AD, so this one's in compression. And then some of the forces in the horizontal direction equal 0. We have RBC and the horizontal component of RAD. So RAD cos 45, or RAD over root 2. Solve for RBC and we get 3 kilonewtons tension. And just to show that you can take a cut through two members, but it ends up being the same as the method of joints in practice. Take a cut through members AB and AD, put in our forces. So this one has to be acting upwards because of P1 acting downwards. And then because we've got a horizontal component to the left here, this one must be to the right. Label them. Sum of the forces equals 0. So RAD over root 2 equals P1. And then just moving up root 2 over to the other side. So we get 3 root 2 in compression. And then sum of the forces in the horizontal direction equals 0. RAB equals RAD on root 2. Get 3 kilonewtons, and that one's in tension. Using method of sections here, right, although because it's only through two members, we've only got two unknowns and they all pass through a point. We don't use a moment equation, so in reality it ends up being equivalent to method of joints. We've calculated the forces multiple times to check our solution, and we've got the same as before, and a good practice for doing both methods. All right, so that's the end of the problem. Hopefully that was helpful and enabled you to see how to analyze trusses in multiple different ways. Don't just rely on the same way all the time. Don't just do what the textbook problem tells you, but actually think about the fact that if you're really going to have to analyze and or design this truss, you've got to find the forces acting on all of the members and at all of the joints. Practice doing that. All right, that's it for now. See you in the next video.